So this lesson is called Part 4 of Factoring or Solving Quadratic Equations by Factoring, even though, and you'll note this, we're not solving any equations here. We're simply factoring. We're factoring things that look like a times something squared, a function of x, plus b times that function not squared, plus c. So I want to start with this. I have no doubt that everybody can factor this. This is not in your notes. We're just sitting back and thinking. I have no doubt that everybody can factor this. You would say, well, the coefficient of the first term is 1, so this is what Mr. Way would call a basic quadratic expression. There's no equal to 0. We're just factoring. And what you would do is you would put an x here, and you would put an x here, and you'd find two numbers that multiply to give negative 40 and add to give negative 3, correct? Can you find those numbers for me? 5 and 8. I like that you said 5 and 8. The numbers are 5 and 8. We'll sort out the negatives once we write them down. Okay? We're looking for two numbers that basically multiply to give 40 and have a difference of 3 because of that negative 3. And I hope you would be okay with that. Okay, so imagine now I teach you that. And then I go, okay, next day you come in, factor this. Is this any different? No, you're still going to put two sets of brackets. You're still going to have this quantity that's being squared here and here. And you will have plus 5 and minus 8. Bear with me. I know that many of you will pick up on this right away, but things can get complicated here. What if I gave you this? And let's face it, x or t is just a series of squiggles on paper that means something. It stands for something. That's the nature of algebra. Well, this would factor into that, correct? So whatever is being squared is just a variable that in the second term is not being squared, and in the third term doesn't even exist. Now these are all with a equals 1, but it doesn't change the fact that this is like saying we're learning how to factor that. It's just that it's not going to be x, it's not going to be a club, it's not going to be t, it's not going to be a puppy. But if it were, that's what it would be, correct? So what we're going to have to do here is, no matter how complicated it looks, we're going to have to think of that thing being squared as a single item that goes in those two places. And this is a very basic example that I'm showing because, again, these are 1. If it's not 1, then we have a more complex expression to factor. You get the idea, right? I don't have to repeat this. This would be bizarre square minus 8 times bizarre square plus 5. Okay. So let's factor this. I want to back up and show you something or say something. Is this a quadratic expression? This thing, yes. This is what we would say. You don't need to write this because it will sink into your brain quite easily. This is quadratic in x. That's what we would say. This is a quadratic expression in x because x is the thing that's being squared in the first term. X is the thing that is raised to the 1 in the second term, and x is the thing that's raised to the 0 in the third. X to the 0 is 1. This would be quadratic in t. It's a little more nuanced than saying squared to the 1 and 0, and we'll encounter that in a bit. But that's basically the idea. This is quadratic in club. This is quadratic in puppy. This is quadratic in weird square. So this is quadratic in 2x plus 5. And when we factor this, we recognize that this is like this, isn't it? So let me cut to the chase and factor this, and then back up and show you what you can do if you need to. But my expectation here is that you look at this and say, well, I need a 2x plus 5 here and a 2x plus 5 here. And then I need, oh, look at that, two numbers that multiply to give negative 40 and add to give negative 3. That would be positive 5 and negative 8. And I just want to point something out to you right now before we go any further. That I hope you would agree, when I multiply these two things, I get this first term. That's my f first. When I multiply these two things, I get my last term. What happens when I multiply my outer? Well, I get negative 8 of the 2x plus 5s. What happens when I multiply my inner? I get positive 5 of the 2x plus 5s. So now what's happening is these two, all of this outer and inner, gives us this middle term, right? So it's no different than having puppy or t or even x. It's just that the thing that it's quadratic in is a little more complicated. So I'm going to get rid of this. This was just me explaining things. Are we okay with getting to here? So the difference is when you do something like factoring with a simpler thing, you factor it, you write it down, you're done. But here we see that there is some simplification that can occur in here. 2x plus 5 is 2x plus 10, because 5 plus 5 is 10. 2x plus 5 minus 8 is 2x minus 3, because 5 minus 8 is negative 3. Okay. Now I'm going to pause there. Everything I have written, maybe what I will do, will it fit? It'll just fit. Everything that I have written there, with the exception of this, is what I would expect you to be able to do in an academic high school math class. And if that's difficult for you right now, then there is something we can do. I can give you a crutch to lean on until it sinks in. And the crutch is to say this. And very few people need to do this, but if you need to do it, by all means do it until you really understand this. You recognize that this is something connected to, say, a squared minus 3a minus 40. And you say to yourself, well, I can factor that. But what you have to realize here is you've just let a equal 2x plus 5. And I hope that most of you, when you see this next step that I'm going to write and then the next step, you'll go, I don't need to do that. But if you do, you do. So you say, well, I'm going to factor this instead. Oh, that's child's play. Correct? But then you snap back to reality and you say, wait a minute, the question didn't have a. I replaced 2x plus 5 with a, so let me put that 2x plus 5 back in there. And you're going to get 2x plus 5 plus the 5 and 2x plus 5 minus the 8, which is where we landed here, right? See, where this is going, everybody, is eventually, like in Math 30, you'll have to factor things like that. It's written a little bit differently in Math 30, but I don't want to add more than I need to here. So you have to be able to say, oh, this will be sine of x minus 3 times sine of x plus 2, because negative 3 and 2 multiply to give 6 and add to give the negative 1 in the middle coefficient. So this is why we're learning this. It's so that when you get to 30, you have to be taught it from the beginning. Anyway, we get to here. We are not done. Why do you suppose we're not done here? When you are asked to factor something, there's an implicit underlying idea that says factor completely. And I don't know if you remember this from Math 10C, but sometimes you'd factor something and you'd end up with more to factor. Is there anything else I can factor here? Sawyer? All right. I can factor the 2 out of the x plus 10. That's right. And that means 2 was a common factor of this thing, but look at the original expression. There's no way you can guess that 2 is a common factor of that mess, because it's more complicated. What this means is if you were to expand this all out, which I don't want you doing, you could take a 2 out. So that's the answer. It's very similar to me asking you to factor, and we may encounter this in an example today, p to the 4 minus 16. Is this a difference of things? Yes. Is p to the 4 a perfect square? You're hesitant on that. P to the 4 is a perfect square of p squared. P squared squared gives you p to the 4. So I can factor this into p squared plus 4, because 4 is what's squared to get 16, and p squared minus 4. Are we done? No, because p squared minus 4 is a difference of squares. Now, I could have made this 256, because then it would go into 16 and 16, and then 4 and 4. So my point is, when you use some step in factoring, look at what it gives you, because you may be able to factor further. Let's try another one. Okay, so this is like 5r squared minus 5r minus 100. I am not going to be rewriting it that way. I'm just pointing out that if you need to, you can factor this instead, and then when you get to what you think the end is, change the r back to 3x minus 2. There's a common factor of 5. What do I have left? 3x minus 2 squared minus 1, 3x minus 2 minus 20. I like the big brackets here because otherwise I have round bracket, round bracket. Now we can factor that quadratic. We need to put a 3x minus 2 here and a 3x minus 2 here. This set of brackets I'm going to put is not necessary. But it helps some people ease their way into what's going on here. And then we are looking for two numbers that multiply to give negative 20 and add to give negative 1. Well, that's negative 5 and 4. So minus 5, and plus 4. And, you know, now when I look at it, those green brackets are really, they're not only are they not necessary, they kind of get in the way, don't they? They kind of clutter things up, but that's okay. We've got 5 and then 3x minus 2 minus 5. That's 3x minus 7. And then we have 3x minus 2 plus 4. And we're done. Negative 2 plus 4 is 2. We're done because, holy smokes, it's 1/4 already. Okay. We're done because we can't factor anything further. Well, that sure changed quickly, didn't it? Get the hang of this binomial squared kind of thing, and now it's like, what's going on here? Is this quadratic? Something is quadratic, and I'm not going to worry about the a thing. Something with a leading coefficient of 1 is quadratic. If you can write it as something squared plus a number times that thing to the 1 plus a number. This is quadratic. It's quadratic in x squared. What really makes this quadratic, listen everybody, is not that the first term is squared and the second is to the 1. It's that the first term has a variable that's even and the second term has a variable that's raised. I shouldn't have said that. The first term has a variable that's raised to an even number. The second term has that same variable raised to half of that even number. Because if I put x squareds here and here and numbers here and here, do you see that foiling it out will give you a number for the last term and x squareds for the inner and outer? Okay, so we just look for two numbers that multiply to give 36 and add to give negative 13. That's negative 4 and negative 9. And I would just ask everybody to mentally FOIL that out and convince yourself that you're going to get x to the 4 minus 13x squared plus 36. Okay, because x squared times x squared is x to the 4. This, by foiling it out, you might gain an appreciation for what I mean by saying this number has to be even, this number has to be half of it, and then there is no variable in the last term. So are we done? No, these are both differences of squares. This factors into x plus 2, x minus 2, and this factors into x plus 3, x minus 3. Now we're done. Well, common factor of 2 leaves us with x to the 4 minus 5x squared minus 24. Is this quadratic? Yes, because the exponent on the variable in the first term is even. The exponent on the variable in the middle term is half of that even number. And then the exponent on the variable in the last term is 0. There is no variable there. So this is going to factor into an x squared and an x squared. By the way, the b squared minus 4ac trick still works. I think, and you can maybe check, because a couple of you I see are checking, I get 121. That's correct. So somebody's confirmed it. And that's a perfect square. What two numbers although it's probably just as easy to factor it, to find those numbers, to convince yourself it's factorable rather than do the b squared minus 4ac thing. That's it. X squared minus 8 is not a difference of squares. E. Oh, you can take a 2 out. N to the 6 plus 4 n cubed minus 21. Is this quadratic? Yes, because the exponent on x in the first term is even. The exponent, well, n. The exponent on n in the first term is even. The exponent on n in the second term is half of that. And then there's no n's in the last. The idea here, this whole half thing, is because the thing you square to get n to an even number is n to half of that even number. So that'll give me my n to the 6. My outer and inner now are going to be n cubeds. So I just need two numbers that multiply to give negative 21 and add to give positive 4, and I'm done. I'm going to pause here for a minute. Does this form a big part of what you expect to see on the exam in this unit? No. Is it important in math? Absolutely. You're building those math muscles. I talk about that a lot, that it's not always just about you're going to need to know how to do this for an exam. It's about getting better at math so when the things you do need to know crop up, you can handle it. Is this quadratic? Sure. So we factor it in the same way we would if it were just squareds into the 1. By the way, there's no common factor, so you need to use trial and error. What do you put in the first two positions? Well, 5y squared and y squared. Not just y, because we want the product to be y to the 4. Are you seeing my point here that if each of these are y squareds, my outer and inner product will be y squareds, which is what we want? Okay. So now it's trial and error. It's got to be a 4 and a 2. I mean, I said 4 and 2, so I'm just going to put them in this particular order that I said them in. I don't know that that's right. How many of you, when you do this trial and error thing, sort it out in your head and then write it down? Okay, a few. Most of us, I often need to write it down. And then I go, well, this is 4y squared. This is 10y squared. Sorry, Charlie, doesn't work, does it? That's not going to give us 3y squared, so that's why we use an eraser in math. I try the other way around. I doubt it will be 8 and 1. If this doesn't work, then it has to be 8 and 1. But, ooh, it's going to be 8 and 1, isn't it? Rats. Sooner or later, we run into that case where, oh no, choose numbers that are closer together. Not in this case. I think 8 here and 1 here with a positive and a negative does the trick. And finding those numbers just because it's y squared and y squared doesn't change how you find them. Are we done? One more step. Y squared minus 1 is y plus 1, y minus 1. Are we good with that? So that's f. Of course, from f we go to I. I don't know. Is it quadratic? Yes. By far, most of the ones we encounter, 99% of the ones we're going to be working with, will be squareds into the 1, and then the constant. But you are going to encounter this sooner or later. No common factor. So I need q cubeds, q cubeds, doesn't sound right, in the first two positions. One has to be 3q cubed, and the other has to be 1q cubed. I'm going to go out on a limb and say that you should understand why these will both be negative. It has to multiply to give 6, and then your middle term is negative. So it's probably 3 and 2. I'm not going to put a 3 over here with the other 3. That would create a common factor. Let's see if this is right. Well, that's not right, is it? Oh, yeah, it is. No, it isn't. How many of you figure you can get negative 7q cubed out of that? See, you might do this, right? Will that give us negative 7q cubed? What's wrong with it? It'll give you negative 6, and you don't want negative 6. So another one where it's going to be 1 and the number. The number pretty much has to go there. Is this thing even factorable? Oh, good. I like that you grabbed your calculator. I don't think it is. You want to do a b squared minus 4ac thing. Oh, no, it's going to be negative. It's not even a positive number. 49 minus 72 is negative 23. But regardless, I'm going to start calling that thing capital D, okay, for next week. It has a name. It's called the discriminant. Not a perfect square, not factorable. We don't have to do anything there.